The unique 4711 octahedral monoicosahedron was set up in my first visit to Gathering for Gardner, which was G4, G7. At that point, I looked very hard for a favorite example that had 7 in it and found something where the square root of 7 was the key, the largest number. And I knew I would come back for G411 because the descendant of that is exactly what we're going to talk about today. The idea of the problem is a really interesting one. Where do you get your problems, people ask you, and the secretaries sometimes give them to you. In this case, I was a postdoc at Harvard. I came in, Mary Wilson was making Christmas ornaments. She said to me and to Andy Gleason, who was there, opening mail, what you call one of those ornaments with 20 triangles, 5 at each vertex? And we both knew the answer, okay? And the follow-up question she said was, do the triangles have to be all equal-sided? I think somehow or other that, she felt it was easier if she had a little leeway. And of course, immediately, Andy and I took out an envelope and did a back of the envelope computation to prove that, yes, indeed, it was quite possible to solve a problem, that is to say, do a icosahedron that had scalene faces, all the same. A monohedron, this is a term that I didn't, my student, Ezra Miller, decided to call them monohedra because they all have the same, they're defined by the same face. So an obvious monohedron would be what you'd get if you take one of the things we've seen several times already, a triangle and cut it up into 4 congruent triangles. And then from that, you can easily, you can solve that problem. Here we are. Okay, there. Okay? You can make a monohedron very easily from any triangle, it turns out. Okay? That's a little strange, though, if you think about it. But let's go and not spend so much time on the triangles or the octahedra, which are the examples you would give to a student. The nice thing about having something at that point, at that time, in that day, was that I had 2 classes, one which was math for non-mathematicians, and one which was a graduate seminar in abstract structures for embedding submanifolds. I could use the same problem in each of those classes. And indeed, if I'm giving you anything as part of the gift, you could just sit down and work on that problem for the rest of the time you're here, or the rest of your life. It's really a very interesting problem with, as it turns out, some subtlety to it that leads to some interesting ongoing research. So I'm going to talk about it a little bit. The first thing would be, can we switch over, please, to figure out what has to happen at each vertex of an icosahedron. Of course, you have 5 edges coming out, and it's a combinatorial problem that if you're going to label them A, B, and C, then A, B, and C, then this one can't be A, but it could be B. You get it. Okay, so here, this can either be B or C. I'll make it B, and we'll get C. So you always get 2 of one letter, 2 of another letter, 1 of the third letter. And that gives a really interesting configuration because there's some geometry that happens. It's not just a combinatorial problem. The geometry that you get tells you that if you look at an orientation, ABC, that you have ABC there, but that's the only place you have ABC in that configuration. All the others are the other way, ABC, 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 ABC. So every vertex has exactly 1 triangle that's oriented differently from the other. You don't notice this if you're doing regular octahedra, obviously. I mean regular dodecahedra. But you do notice it here, and that gives you an interesting way of giving a decoration to the objects we're working with. Do I only have 1 minute and 20 seconds left?
Yes.
My gosh. Okay. That's impossible. Okay. Well, you're going to figure it out. The regular tetrahedron metric is the obvious one. And A.D. Alexandrov is the person who really proved some years ago that you could solve this particular problem for the tetrahedron, for the icosahedron, if in fact you allow yourself to figure out whether the angles are, well, acute or right or indeed obtuse. Here's, for example, a tetrahedral metric with obtuse triangles. You can solve that. You can find a unique convex body in 3 space that gives that metric. Of course, you see the solution. Well, you re-subdivide and don't use the original triangles. You use the triangles that you get by putting in the opposite diagonals, so you get the original tetrahedral metric. That business indicates that an abstract theorem doesn't really tell you, an abstract theorem like Alexandrov's theorem tells you that if it could come from a convex body, it does come from a convex body, and then Cauchy shows you that it's unique. Charles Strauss and I, from the beginning, started working with interesting problems. This was the second one we worked on. I talked about the first one last time. And indeed, Charles unfortunately died earlier this year, but we had published a paper about this at some time. And the publication indicated that you could look at the space of all triangles. There it is. It's up on the board. And in it, you can find the right triangles. You can easily show for the icosahedral situation that you'll have, if you consider the angles alpha, beta, gamma, that you'll have at each vertex, because of the configuration I indicated before, you'll have an alpha, a beta, a gamma, and then 2 others, either 2 more alphas, 2 betas, or 2 gammas, which shows you that you can't use the icosahedral metric that comes from an obtuse triangle. You can, however, use a right triangle, and that's what we're going to do, because what we found was the unique right monoicosahedron. That's Ezra Miller's notation, and this is the one I talked about. In fact, you already had it when you were here, G4, G7, as your gift, and you can see that it has very nice configuration with a square root of 7 in the middle. Ezra Miller used this as his senior thesis at Brown University. He's a full professor at Duke right now. And icosahedra constructed from congruent triangles was the article that he wrote in 2000, where he very kindly proved a conjecture of Banchoff and Strauss. We had stated that it was unique without proving it, and he found the proof of it. Here's the right monoicosahedra. And the unique one in this configuration is exactly here. That's Ezra Miller's favorite one. But the unique one is obtained right on the, by pasting these together. This is 2 root 7 root 11. And so that's enough. I actually want to give this to the Pope, because if you Google Pope polyhedron, you'll see that the Pope is using a polyhedron as his example. So this is a monohedron, because he's a monotheist, and possibly called the Papahedron. In G4, G10, I did a 10-cell ornament, and John Conway very kindly talked to me about that when we first did it. And finally, we thank Martin Gardner for all the inspiration. Thank you.